So 3.5 day 2, there is more material. There's this 3.5, they easily could have broken up into multiple sections, but they didn't, so I did. Okay, I don't remember which page this is on in your book, but the first thing that we need to talk about are derivatives of trigonometric function, inverse trigonometric functions. We already know the derivatives of trig functions. This is going to be on page 214 in your book, page 214. I'm going to reveal them a little at a time instead of all at once. So whether you want to write them down or just screenshot from your book, it's up to you. So the first two, the derivative of the arc sine or the inverse sine, and the derivative of the arc cosine or the inverse cosine. Okay, they're basically the same. That's why I put them together. Sine's positive, cosine's negative. 1 over the square root of 1 minus x squared. And these are derivatives that you need to memorize. Again, like I've said before, if you really want to see where they come from, you are welcome to look in the book and they go through the proof, but it's just not worth our while, in my opinion. Okay? All right. Next is the tangent and the cotangent, the arc tangent, inverse, okay? So this one, these don't have square roots. 1 over 1 plus x squared, cotangent is just the negative of that. And I save the worst for last. And the worst for last are the secant and the cosecant. But again, they're paired together, right? So this is the oddest ball of them all. Right, the derivative of the arc secant is 1 over x times the square root of x squared minus 1. The derivative of the arc cosecant, or the inverse cosecant, is the same but negative. So those are all of them. All right, we're just going to run through a bunch of examples, and then I'm going to teach you about derivatives of actual inverse functions that are not trigonometric functions. Okay. So the first one, pretty straightforward. Square root of y equals the square root of the arc tangent. Okay. Of course, if I had just said find the derivative of the arc tangent, then we would look at the formula and we'd just write down what was there and we'd be good. But we can't do that because this arc tangent is underneath the radical. So we need to be thinking about it like this. Y equals the arc tangent to the 1/2 power. Because what we need to do is the power rule. But then what else do we have to do? Chain rule. Because that inside function, that there is an inside function, we're going to have to use the chain rule. So go ahead and try this one. Here's how this one starts off, okay, right? So I just use power rule, bring the 1/2 down, reduce it by 1. Then I have to take the chain rule of that inside here. So then I have to then also take the derivative of this, which is the 1 over 1 plus x squared. Okay? From here, I need to kind of put it together, though, and make it a little more simplified. So here are the things that I can do with it. Right? This can all go down. The 2 is already down, and this is already down. So really on top, there's a 1. Okay, and so I like to always put not ugly things in the front. To me, this is an ugly thing. Would it make a difference if these two were flipped around? Of course not. It would not. Don't forget your y prime. That's kind of important. That's where all of a sudden all those arms went up. There we go. How's that? Or we could have also said any of those work. Yeah, I sure did. I lost my 1/2. Good call. You were all ready to pounce. I love that. Like, ha, we got him again. It's fair. I appreciate that. Okay, questions on that? How many had it? Or some variation of that? Very good. Next one. What's involved with this one? What? What do we gotta do? Product rule, right? I got two things being multiplied together. All right, let's take a look here, see how we start off. Whew, there's a lot there, right? So, this is the first function, so that's why it's just copied. The derivative of the arc secant, 1 over x times the square root of x minus 1, x squared minus 1. Then the second function, and then derivative of this. All right, so here's what's going on here. So the 1/2 comes down, reduce it by 1, and then I have to take the derivative of the inside function, which is 2x, okay? How many had that so far? Good, all right. Now here's a matter of trying to figure out how to clean this all up. Make it into something that's a little more simple. What I'm going to start with is trying to push this together into one fraction. So in reality, this just goes up top. Down here, okay, remember this is not the secant of all this. This is secant, arc secant times this. So this can go down, the 2 can go down. Actually, the 2's can cancel. 1/2 times 2 is 1. The x is still up top. The arc secant is still up top, and this goes down. So here's what that looks like. So the 2 and the 2 cancel. I took this x and I put it in front. And then this goes down. Now, got a couple more things we can do here. What's one thing you notice we can do? Cancel the radicals on the left, absolutely. That is the same as that. It can go away. Okay. Which leaves me with 1 over x here. I'm not going to be able to do anything with this. Could I add those together and get a common denominator and that kind of thing? Sure. Is that going to be better than this? I don't think so. We would have this on top plus x squared secant x all on top, and then on the bottom have x root x squared minus 1 on the bottom. Yes, I know back in the day we said no radicals and denominators. That's bad, bad, bad. We don't say that anymore. College Board doesn't care. AP exam doesn't care if you have a radical on the bottom. So you can erase that whole idea from your mind that it's a bad thing to have it down there. Okay, just like it's like the, we say, what's the one, like 2 over the square root of 3. That comes up a lot. Or square root of 2 over 2. 1 over the square root of 2 is fine. That's fine in calculus. Okay. All right. Questions? Other questions? Next. We have 2 more to do. This one's not that bad, right? We got a little chain rule going on inside that tangent, but shouldn't be too bad. Give that a shot. Remember, the derivative of the arctangent is 1 over 1 plus x squared. Okay? In this problem, what is acting as our x? x squared plus 1 is acting as our x. So in reality, what I have is y prime equals 1 over 1 plus this squared. Since x squared plus 1 is acting as our x. But then I also have to take the derivative of this inside function, which is just 2x. Okay? I saw a lot of you write in front 1 over 1 plus x squared. Remember that this right here is acting as our x. Those are not, you can't separate them. Because those parentheses are there, it's saying the arctangent of that whole thing. So that's why it goes here where our x would be. And then the chain rule piece has the 2x. I can combine them together and we're good. We don't need to multiply the bottom out. It's not going to cancel with anything on the top anyway, so there's no reason to do that. Okay? One more before we get into the inverse functions. Huh? Well, these are just trig inverse functions, just regular inverse functions that are not trig related necessarily. Theta is our variable in this problem. So keep in mind that our inside function is there's almost like there's two inside functions. There are. This is serving as our x for this problem. But then when I have to chain rule it, I have two inside functions for this. So keep that in mind. All right. So here's the way I rewrote it. This is for me. You don't have to. Okay. But this is how I rewrote it. That you could have left that arc sign. I definitely think you should rewrite this. Now, the derivative of the arc sign, 1 over the square root of 1 minus x squared. In this case, this is all serving as our x. Okay? And then I have to go chain rule from there. So this all serves as my x. We'll clean this up in a second. So now I have to take the derivative of this, which is 1/2 sine theta to the negative 1/2. And then I have to take the derivative of sine theta, which is cosine theta. So that's, like I said, where we had a double inside. This all is inside, but then I have an inside of inside. All right, now I got to attempt to clean this up a little bit. All right, first of all, the easiest thing to do is realize that I have a 1/2 to the second power. Multiply those together, that gives me a 1. Okay, question. Okay, next, let's see. The 2 can go down. This can also go down. The cosine can go up. All right, so this 2 went down. This square root of sine went down. This went down, and the cosine went up, and we're done. You can't distribute. I mean, you could. It's just not going to get you anywhere. I could make this the square root of sine theta minus sine squared theta, but it doesn't improve our fraction at all. So we're good to leave it just like that. Okay. I know one of the issues you're having is how far do I need to go, right? And my best recommendation is to try to combine things into one fraction when possible, at minimum. If you can reduce after that, then try to do that. But if it's not going to reduce, there's no reason to do that. And so that's something that I consider before I even move on to the next problem. Like, can I do anything more? Because in this problem, I can't. Not that will get me anywhere beneficial. All right. Let's move on to the derivatives of any inverse function. Okay. Now we're not talking about just trig functions. We're talking about any inverse function. And so I'm going to put something on the screen that I would like you to take a picture of rather than try to write down. Okay, there's a lot of information here. So yeah, take a picture of that, and then I'll go through it and explain what it all means. There's a lot of information here, and some of it is just not very useful, but I took it straight from what you see in the book. Okay, f is a one-to-one differentiable function. Therefore, it has an inverse f to the negative 1. That's how we designate an inverse function. What this is saying is if I take the composite function, the derivative of f at this particular value, the inverse of a, then the derivative of that is equal to 1 over the derivative of the inverse. Again, the math looks crazy. The bottom line is what this is trying to say, because these two things are reciprocals, right? The derivatives of inverse functions are reciprocals. That's what you need to know. The derivatives of inverse functions are reciprocals. So oftentimes you're going to see problems like what I'm about to show you, where they give you part of it and you have to use it to find the rest of it. Okay? It relies also on the idea that you understand that when I have a function that is, let's say it's like this, that the inverse is like this. Okay, that those numbers switch for the inverse, right? We switch the x's and y's, that's where we come up with the inverse function, generally speaking. Okay? So this relationship is going to be really important in order to find the derivatives of the inverse functions. Okay, understanding that. Okay. Here's the first example. And these problems will regularly look like this. Okay? If f of 3 is 7 and the derivative of f at 3 is 1/6, find the derivative of the inverse at 7. Now you may be thinking, oh, well, you just told us the derivatives of inverse functions are reciprocals, so 6. The derivative at 3 is 1/6, so the derivative of the inverse at 7 must be 6. And the answer is yes, but you need to know why. Okay? And so we're going to use the formulas that we're given. And I'm just putting the formula back on the screen for me. You already have it in your notes. Okay, and I just want to show you how to make this work. Now, this is me taking this formula and plugging the 7 in for A. Because this is what we are trying to find. This is what we are asked to find. Notice here what it says. The derivative of f at the inverse at 7. Okay. Now, because of this, since f of 3 equals 7, then the inverse of 7 equals 3. Right? This is just what we talked about. The function at a equals b, then the inverse at b equals a. Now, this is this. Okay, so in reality, what we're saying is that what we're looking to find is 1 over the derivative at 3. Well, they gave us the derivative at 3. So it is, in fact, 6. Okay? If you went and just said 6 because you're like, oh, he said about reciprocals, without using the formula, I would caution you against that, because if that was part of an FRQ, you're not going to get all the points. Probably get one of the points if there were 2 of them there, but you want to write some of that information out. Now, a more common type of problem that you're going to see, which becomes a little more challenging, is this. This is the last one we're going to. Okay. In this case, we're looking for the derivative of the inverse at 2. And the problem here is that's all the information they give us. We don't know what the x value is for the original function when y equals 2, because that's what this is saying. Okay? For the inverse function at 2, that was the original y value for the function. And so we need to find that original x value. And so one of the things that you're going to have to do on problems like this, again, we're talking about this is my formula, right? In order for us to find what we're looking for, we also have to find what the function is at 2. And for the inverse, this is actually the y for the function. So what we're going to do is we're going to set our equation equal to 2. And then that will tell us the x value that goes with this problem. And that x value then will give us this. Now, you're going to need your calculator to do this part because oftentimes these are not factorable. Okay? So you need to know how to find zeros on the calculator. All right? Now, you can try to do that now. We don't have a lot of time. And if you need help using your calculator to find zeros, let me know. But I'm going to skip past that right now just for the sake of time, because this is where you're going to go to your graphing calculator and you're going to find the zeros. All right? And I'm just going to tell you what zeros are. X equals 1 is the 0. So let's understand what this is. Okay? For the function, x is 1, y is 2. For the inverse, they flip. So the inverse x goes with the function x. Okay? So here's what we're talking about. And here's where we've written it out. So this means f of 1 equals 2. Okay? This is what we've proven. X is 1, y is 2. Which means if I flip it, then I get the inverse. Okay, the inverse at 2 is 1. Which means all of this right here is 1. And this is where I say it's a little tricky. So now it's just a matter of finding the first derivative of f. Well, we have f. And we can find the first derivative of f. And then we just have to plug the 1 in, and we're done. So here's the first derivative. Okay, just power rule. 5x to the 4th minus 3x squared plus 2. Now I need to plug the 1 in, and I get 4. 5 minus 3 plus 2. Which means the derivative of the inverse at 2 is 1/4. And there was no way for you to just look at this problem and go, oh yeah, flip it like we did the last one. There's nothing to flip. We have too much missing information, but not enough missing information that we can't do the problem. Okay, we have enough information to do the problem is another way to say that. Okay, the idea of inverses in x and y's, and then the x and y's flipping for the inverse versus the function, that's the key idea here. If you need help finding zeros on your graphing calculator, please let me know. I'm happy to help you with that. But this formula is going to be important for your success on these problems, okay?